So in your sample, so if you go to sample data and gene expression data, you will see this file here, NHDF time course experiment 1+2 filtered version 3. And if you just drop that into there now, so now we've loaded this data in, you'll see this view here, will you? Okay, so unique identifier, as I mentioned. We have no sample class sets here. Could have put them in, but I haven't. We've got a lot of class information, probably far too much. I didn't really prepare this for this course, but we've got lots of information that we might want to put into all of these sets, including whether they're transcription factors, whether they're various other things. The other thing just to watch, that if you have a numerical value in your last column, so you see how it's colored things green, red and blue. The reason it does that is what it's looking for is that it's looking for the first set of numerical data. Okay, now in this case this Affymetrix probe IDs is just a number, it doesn't have the underscore AT, and so that would be recognized as a value if it wasn't that. So if for some reason the tool, so you need to just check that it actually is recognizing the data as being data and the annotation as being annotation. And if it doesn't, you can also change that. So I can make the second line now the data by moving that around here. So you can change things here. So the other thing that we can do here is that sometimes, especially when dealing with very large data sets, we want to actually, so what this 0.7 does here, it defines the minimum correlation that it's going to save. Okay, so as I mentioned, the correlation calculations are huge. If you saved all the data, you'd fill up your desktop very quickly with memory. It would save it. So it's only saving the top correlations, and the correlations that we want to save might be lower than 0.7, but the default is 0.7. Okay. Now the other thing to mention is pre-processing. So that if you haven't changed your data from log2 data, you can do here. Okay, I can make it anti-log. So when that comes in, it'll take your log2 data and convert it to natural scale data, or if you've put log10 in. And the first thing I'm going to do is I'm going to use this, it's not, because we've got natural scale, is I'm going to transpose it. So I'll explain what I'm doing here. There's two ways of looking at data in biolayout, and the first one is to transpose data. So I'm actually asking here to plot the sample-sample correlation. Okay, how similar, so this is what I mentioned about your first QC step. The first thing to ask is, do things cluster together like I would expect them to cluster? Okay, and let's try the GNF data set. Okay, so if we drag that in here, we've got the GNF data set. We'll go to pre-processing, we say transpose, and then say OK, and it has done it. Good, OK. Right. So did you get that for try the GNF dataset? It's actually a better dataset for this potentially. So what you're going to face when you load data in, you probably saw a quick calculation there. So what it's doing now, so there's the GNF dataset is the dataset which we developed this for originally, because it was the one I could least understand. So this basically is a dataset of 61 mouse tissues, which was analyzed, I think it was published in 2004, and basically it was the first expression atlas. It's tried to define the entire transcriptome of the mouse, and it's still a nice data set. Okay, so when you load it in this mode, it gives you two plots. So any way you load in data, it's going to give you this plot, first of all, and this represents the number of nodes. So there are potentially 122 nodes here. Okay, so there's 122 samples. We've transposed it. We're asking how similar are the samples to each other. Therefore, there are 122 nodes here. And so what this says, that this line is now flat. It means that it doesn't matter how much lower you go with your correlation, what you're actually seeing is only those nodes which are, everything has been correlated within the network above this point here. So you'll notice that as I move this around here, then the thing that's changing at the bottom here is the number of edges. Okay, 230, 140. Yeah. So what I'm going to do is I'm going to put it at 0.7 and show you the difference between what this effect is, because it's kind of easier to understand here. So if I look at it at 0.7, and I'm going to go back to 3D. Actually, these sample graphs are often quite nice in 2D. You can, and I'm just going to change my edges, make them not proportional to weight. Well, I might make them proportional weight, but I'm not going to make them. You can see I've got a graph. So each one of these nodes represents, I'm going to go back to just reload it again in 3D, transpose it, say OK, add a 0.7, and we get that. Okay. So now we've got a graph. So this graph is still a very small graph, but you can see already it's getting structure, it's getting complexity in how things are grouping. So in this case, each node in the graph represents a different sample that we put in. Okay, so 61 different tissues in replicates. So each one is essentially a tissue. So if we look at the actual names again, we can begin to see the names in here. Now, even without looking too hard, you can see that actually replicates are grouping together. The eye sample with replicate 1 is grouping with the eye sample of replicate 2. Testes, testes, liver, liver, kidney, kidney, placenta, placenta, spleen, pancreas, spleen. Probably the spleen was contaminated with pancreas. But you can see that the samples are now beginning to cluster according to how we wanted to expect. So I just want to just go into here a second and hide all the shot. Right, so just in graph speak, I'm just making my edges a bit wider because you can hardly see them. Okay, so just a bit of graph speak. This is a graph, okay? This is a component of a graph. So you'll often hear people calling about, oh, I've got this little graph here. Well, that's not a little graph, it's a component. I know it's pedantic, but it's actually, it's a different name. Okay, so that's a component of a graph. The whole thing is the graph. So what a component is essentially a bunch of nodes which are related to each other, but they're not related to anything else within the graph at that threshold. Does that make sense? So these guys share a relationship, but the eye has no relationship to any other tissue at this threshold. Now, we're going to go into sort of the first basic thing with this, and this is clustering. Okay, so I hope, and I'll try and show this by disabling the nodes. You can see that this graph has structure. Okay, so that what we've got is a series of things that share relationships with each other, and that those relationships are not some sort of random relationship matrix where everything is kind of related. It's not a small world matrix. This is a matrix where we've got a bunch of things here that are highly correlated with each other. We've got a kind of more looser structure here, and we've got this whole range of things here which are related to themselves but nothing else within the graph. So it's a structured graph. And it's this structure that essentially we want to exploit, because this structure is essentially the patterns within the data. So let me just go back to general, turn on my nodes again. Okay, so that is the structure that we want to exploit.